We'll get started, huh?
Yes, sir.
Okay.
இதெல்லாம் முடிஞ்சதா இல்லையா ஸ்கூல்ல? This is over in your school, this chapter. தெரியுமா அது உங்களுக்கு தெரியுமா லாகிங்ல இருக்குன்னு தெரியும். Which chapter is going on for you? Current electricity is over. Okay. Plumber, we'll get started. Shall we? Just every good, sir. நல்லா போச்சு. சரி. Okay, we'll get started. So the next topic that we are going to discuss is self-induction, right? So if we just recollect the topics that we were seeing from the beginning, what were the topics that we discussed? So what were the topics that we discussed? So first we try to understand the whole context of this chapter lies in the fact that if there is a change in magnetic flux taking place, there is going to be a EMF that is induced. Am I right? So when we talk about induction, right? So what generally happens is there should be a relative motion that is existing between the magnetic source and the coil which is picking it up. If there is a relative motion that is existing between them, or even if there is no relative motion existing between them, there is a possibility where the change in one flux, change in magnetic flux in one coil can produce an EMF in the other coil, will also be the cause for this process called as electromagnetic induction to take place, right? Of which one of the important ways in which EMF can be induced is called as self-induction. So there are basically two types of these kind of inductions that we'll learn. One is called as self-induction and the second is called as mutual induction. Okay. So let me give you what that means. Okay. So I have a material here. You're able to see? So this has two coils, right? So I'll show it to people here. This has two coils. Are you able to see? Those are online.
Yes, sir.
Yeah, there are two coils. No, one coil is connected to this red color button. One is there near the LED. Okay. So I'll come there. See. Let me explain what it means. Observe. I can't turn it. Okay. So this coil, which is connected to the switch, right, will have the current generated in it. What is going to happen? When I press this button, there will be current flowing through this coil. You would have seen, right, in many problems we were discussing that there is a coil with n number of turns. So this is the coil they are trying to talk about. So coil is wound around something which has n number of turns, which here there is a copper coil, right? So one coil that is connected to the current source will have a change in magnetic flux taking place through this when you switch this on. And if you see the other coil is directly connected to the LED source, it is not having any power source. Means whatever change in magnetic flux is taking place in the first coil should be able to generate EMF in the second coil. Does it make sense? So that's what the concept states. What does Faraday's law of electromagnetic induction state? If there is a change in magnetic flux taking place in a coil, then there is an EMF induced. You can test that EMF being induced with the help of a light source. So if this, when I switch this on, if the light source is going to glow, then there is an EMF induced. If not, it is not. So in this case, what is happening? Let's try to understand the science behind it. That is more important. So in this case, what is happening? Initially, before I press this button, what is going to be the value of current in this? 0. When I press the switch, the current will grow from 0 to some steady state value. Let's say it is growing to some I ampere. So between that 0 to I, there is a growth in current taking place. So when there is a current flowing through this coil, current will generate magnetic field. So the magnetic field generated by the first coil will get linked with the second coil. Make sense? So what is happening? First current is passing. So current is growing from 0 to a certain value. Due to that increase in value, what is going to happen? Magnetic field will also increase. So when the magnetic field is going to increase, can I say that due to the increase in magnetic field in the first coil, there is a change in flux taking place in the second coil also? And due to the change in flux taking place in the second coil, there is an EMF induced and this bulb should glow. But how long will it glow? It will glow only till the time there is a change in magnetic flux. How much time do you think it is going to? There is going to be a growth in current taking place. From 0 to reach a steady state value, it is not going to be much of a time. So when I press this, are you able to see that the LED is just flickering? Is it flickering? So what does that mean? Means when I press this, the current is growing so fast that the magnetic flux associated with this coil is also changing rapidly. And during the time it is taking, the change is taking place, this bulb is glowing. So this kind of a process where an EMF is induced in other coil due to the change in current, where an EMF is induced in a coil due to the change in the other coil is what is called as mutual induction. You can ask me, the topic that we are discussing is self-induction. Then what do we have to do with mutual induction? Right. Now the question is, as the name suggests, now I hope you got some idea of what is induction. So what is happening? Due to current also, till now we were discussing that there should be a change in the magnet or the pickup coil for this to take place. But now there is another concept here. There is no motion taking place. But what is happening? There is an increase in the value of current in this coil, which is generating an EMF in the other coil, which is called as mutual induction. Why we call it as mutual is because the EMF is getting generated in the second coil due to another coil. It is mutually happening. It is not happening within. But if I forget the second coil, right, and I say that due to the press in this button, I am able to generate EMF within this coil apart from the existing EMF. So what am I going to do? I don't have a second coil. So this coil itself is acting as a current carrying coil and a pickup coil, where the current flowing through this coil is able to induce EMF within the same coil. Then that kind of a process is what is called as self-induction. So for mutual induction to take place, you need a minimum of 2 coils, but for self-induction to take place, it will happen within the same coil, right? Let's try to understand why this is happening. Mutual induction ரெண்டுமே வந்து current carrying. The both should be coils. Okay. So here what is happening? So mutual induction என்ன நடக்கும்னா, we always speak about current, but initially நம்ம என்ன பேசணும்? When there is a coil, you are moving a magnet. Magnet current பத்தி பேசணும். You are only changing the flux. So don't get confused. புரியுதா? So, am I clear? Did you get the context of it? So these are the 2 important concepts you are going to focus in today's class, of which the first topic is going to be about self-induction, right? So listen to this. When I talk about self-induction, right, it is a process, right, where when current flows in a coil, see, let's discuss about the story of this. This is the coil which I showed you here, right? This one, forget about this. This is the coil which is here. And this is the switch, right, which is open. And this is the battery. Okay. So if I put it in a diagrammatic format, it is going to look something like this, right? Now, when the switch is open, what is obviously going to be the current flowing through the coil? What is the current associated with the coil? 0. When switch is open, obviously the battery is not connected to the coil and there is no current flowing. But as soon as you close the switch, what is going to happen? There will be a current flowing from the battery from which terminal to which terminal? Positive to negative terminal outside the battery, right? So due to this current, there is going to be a growth in current taking place. From where? From t is equal to 0. T is equal to 0 is the instance when the switch is open. T is equal to, let's say, some 2 seconds or 1 second. The current has grown from 0 to some steady state value. Within that 1 second, do you accept the fact that there is a change in current taking place? So between that 0 to 1 second is what I'm concentrating. You have to visualize it. So between 0 to 1 second, what is happening? The current is growing from 0 to some steady state value. Am I clear? So when the current is growing from 0 to steady state value, can I say that there is some magnetic field linked with this coil? So if I put it as a sequence, current is increasing from 0 to some value. So when I say current is increasing, can I say it is directly increasing the magnetic field associated with this coil? When magnetic field is increasing, can I say that the flux is increasing with this coil? As soon as the flux starts changing between the 0 to 1 second, what will happen? EMF is induced. That is during which process? When the switch is closed. So if you do the reverse, now you have a closed circuit. So in a closed circuit, what is going to flow? There will be a steady state current. So when I say steady state current, I is going to be constant. When I is constant, B is constant. When B is constant, change in flux is 0. Change in flux is 0. When change in flux is 0, EMF induced is 0. So if I have a closed circuit, now I am opening it. When I open it, what will happen? The current will decrease from steady state value to 0. Am I right? So when the current decreases from steady state value to 0, again, current is going to decrease, due to which magnetic field will decrease, due to which flux will decrease, due to which EMF is induced. Because for EMF to get induced, there is only one condition. What is that? Flux should change. Magnetic flux should change with respect to time. Did you understand what is happening during this process? So now read the statement clearly. When current flows in a coil, it gives rise to magnetic flux through the coil itself. Does it make sense? There is one intermediate step. Current flows through the coil, it gives rise to magnetic flux. Right? So as the strength of the current changes, so when they say change, the current can either increase or decrease. Changes, there should be a change in value with respect to time. When current changes, the linked magnetic flux changes. Current changes, linked magnetic flux changes. Due to which what will happen? There is an EMF that is going to get induced in the coil, and the name of that induced EMF is what is called as opposing EMF. Because what will happen is the EMF will get induced in such a way that the induced current will be in the direction opposite to the actually flowing current. Right? So, listen. So, in this case, when the switch is getting closed, if you see the current in the circuit is going to flow in the clockwise direction. So, in this case, what is going to happen is the EMF will get induced in such a way that the current will be in the opposite direction. Why? Because what does Lenz's law state? What does Lenz's law state? If there is an increase in flux, what pole should get generated? Will it be same pole or opposite pole? Same pole, right? So here, when you close the switch, are you increasing the flux or decreasing the flux? So you're trying to increase the flux. According to Lenz's law, the induced current will be in such a way that it will try to decrease the flux. So what should happen? So listen to this logic clearly, because you will have questions asking what polarity each point is going to be. Which point is positive and which point is negative. For that, you should be in a position to decide it. Listen to this carefully. Listen to my statement carefully. What does Lenz's law state? Lenz's law states if there is an increase in flux, same pole is going to get generated. When same pole is getting generated, is the induced current going to be in a supporting way or opposing way? It will be in an opposing way, meaning here when the switch is closed, the current is growing from 0 to a steady state value. So when current is growing, flux is also growing. So the induced current should decrease it. That is why the current is flowing in the leftward direction. When the current due to the battery is flowing in the clockwise direction, current induced is flowing in the anti-clockwise direction. Whereas for this circuit, If you see, when you open the switch, what are you trying to do? You're actually trying to decrease the flux. When you try to decrease the flux, opposite pole will get generated. In the sense, what should happen? It will try to do the reverse. Since you're trying to decrease the current, it is trying to increase the current. So if it has to increase the current, then the induced current should get generated in the direction of original current itself. So why I ask this question is, if the induced current is from right to left, then this pole is going to be positive and this pole is going to be negative. Don't get confused. This positive and negative is due to the existing battery, but this positive and negative is due to the induced EMF. Whereas in this case, what will happen? This will be positive, this will be negative. Am I clear with that point? Are you able to understand? Let's discuss it one more time. What does it state? Flux increases, the current will flow in such a way that will try to decrease the current. So when you close the switch, flux is going to increase. So induced current will try to decrease the original current. That is why the current is in the clockwise direction. Then the induced current will be in the anti-clockwise direction. What will happen in the case when you're trying to decrease the flux? When you try to decrease the flux by decreasing the current, it will try to do exactly the opposite. It will try to increase the current, means it will start supporting the actual flow of current. So if the actual current is flowing due to the battery in the clockwise direction, induced current will also flow in the clockwise direction. Hence, the polarity of induced EMF in both the cases will change, which you need to decide it depending on the problem. So there are only two questions you need to answer. Flux is increasing or decreasing. That's it. Is that clear? So having said this whole process of generating induced EMF across the same coil due to its own current. So you're actually generating the EMF, you're actually inducing the EMF across the coil due to whom? Are you having any other current? No, it is due to its own current. That is the reason why you call this kind of a process as self-induction. So self-induction is basically a phenomenon that you can actually see. You will be able to sense it. Are you able to understand? So this EMF is also called as self-induced EMF, or sometimes they also call it as back EMF. So what are the three names that are given to it? Opposing EMF or self-induced EMF, or you also call it as back EMF, right? And this phenomenon of what did I state? What is this phenomenon all about? Phenomenon of generating the EMF within the coil due to the change in current, due to the change in its own current is what is called as self-induction. Am I clear with this? Right? Please make a note of it. Mostly you will not use self-inductors. You will use this only, mutual induction only. But we are reading this concept to understand that even during mutual induction, there is a process called as self-induction that takes place. Motors வந்து வேற பிரின்சிபல் அது வந்து டிரான்ஸ்ஃபார்மர்ஸ்ல நடக்கும் மியூச்சுவல் இண்டக்ஷன். அது ஆக்சுவலா நான் காட்டினது டிரான்ஸ்ஃபார்மர். சொல்லுங்க. లేదా The coil and a magnet moves with constant velocity 5 meters per second and 3 meters per second respectively towards each other. Then the induced EMF in the coil is going to be 16 millivolt. Okay. Velocity. So relative velocity in the ether, when they both are moving in the same direction, the relative velocity will be 2. Should we use BBL? அது வந்து mostly EMF use பண்ணலாம், but here you don't have length of the coil. You cannot use that. So the flux has to get changed into Actually, it's going to be a simple formula. The form, but bookல கொடுத்திருக்காங்க. கொடுக்கலையா? Field. என்ன கோயில் எந்த கோயில் வேணாலும் இருக்கணும். Flux is equal to BA cos theta. Theta வந்து 0 degree வச்சுக்கலாம். B வந்து constant. B is changing. Area is constant. When you relate magnetic field to velocity is what the concept. அது யோசிச்சு சொல்றேன் இப்போ. கிளாஸ் முடிஞ்சதுக்கு அப்புறம். Shall we proceed? Those are online, did you understand? So are you clear with the concept?
Yes, sir.
Listen
Yes,
to this.
sir.
Listen. So now we understood what is this phenomenon called as. It's called as self-induction. So I'm going to use some terms. Listen to this carefully. Now, tell me one thing. See, we know that EMF to get induced, it should be directly proportional to which parameter? According to Faraday's law of electromagnetic induction, EMF induced should be directly proportional to the change in magnetic flux taking place with respect to time. That is delta phi by delta t or d phi by dt. Okay, accepted. Now the question is, in this case, the EMF is getting induced due to whom? In this case, the EMF is getting induced due to the change in current. So can I conclude that the EMF induced in this coil is directly proportional to the amount of current that is flowing through the coil itself? Can I state it? Right. So correction. Can I say that the flux associated with this coil is directly proportional to the amount of current that is flowing through the coil itself? So can I say phi is directly proportional to I itself? Are you accepting this? So there is some amount of current flowing through the coil. If there is an increase in the current in the coil, then there is going to be a change in the magnetic flux associated with the coil. So flux is directly proportional to the amount of current flowing in it. Accepted or not? Now, the question is, if I remove the proportionality symbol, what is the constant I'm going to introduce? So flux will be equal to, I'll introduce something called as L, and I'll write it as L into I, where this L is what is called as self-inductance. So it's called as self-inductance. So this is where you might have a confusion. Then what is the difference between self-induction and inductance? Induction is a phenomenon. It is a process that is happening. Inductance is a parameter that is associated with a device called as inductor. Listen to this carefully. Just for you to understand, there are terms like resistance and resistor. Similarly, what do you have? You have capacitance and capacitor. Am I right? So anything that ends with A and CE is a property of a material. So resistance is a property of a material called resistor. So anything that ends with OR is the material itself. So resistor is a device. Resistance is the property of the device. Similarly, capacitance that ends with A and C is the property of a device called as capacitor. Similarly, inductance is a property of a device called as inductor. It is a property of a device called as inductor. Okay. So what an inductor does, I'll tell you. Don't worry about it. Okay. What an inductor does, I'll tell you. But listen to this carefully. Are you in acceptance with the statement that phi is directly proportional to I and phi is going to be equal to L into I? Right. But what is the EMF? EMF is equal to minus d phi divided by dt. So EMF is equal to minus d phi divided by dt, or this is also going to be equal to negative of d by dt of, how much is it going to be? Can I write it as L into I? So L is a constant for a given device. Like how resistance is constant for a given resistor, L is a constant for a given inductor. So take the L outside, minus L into, I'm going to have di divided by dt. Am I clear with this? So what we are trying to say here is, if you want to write the expression for EMF induced in a coil in terms of self-inductance, then it has a mathematical expression of minus L into di divided by dt. Okay. Now listen. Now listen to this. So what did I write EMF as? EMF is equal to minus L into di divided by dt. Right. So L is going to be equal to E divided by di by dt, ignoring the minus sign. So here I know that the minus sign is the indication of Lenz's law that we have already seen. That is the reason why we try to understand what is self-induced EMF or back EMF. We understood the significance of Lenz's law. When the current is increasing, induced EMF will be in the opposite direction. When current is decreasing, induced EMF will be in the same direction. That is the significance of minus. But listen to this very carefully. L is equal to E divided by di by dt, right? Now, if I ask you what is the formula for resistance, what will you say? R is equal to V divided by I. You know this, right? Or I can write it as E by I. Now tell me one thing. If V is kept as a constant, right? You take a resistor and connect it across a potential source of a constant value. Can I conclude the fact that R is inversely proportional to I? Okay, that is a mathematical expression, but I am interested to know what is the device going to do. So what does a resistor do according to you? Resistor will try to decrease the flow of current. So if you take a resistor, you connect it across a battery, the battery will start supplying some energy and current will start flowing. What will a resistor try to do? It will try to decrease it. So if you keep increasing the value of resistance, current will try to decrease. Makes sense? Using the same logic, if I keep the value of E constant, can I say L is inversely proportional to something called as di by dt? If the resistor's job is to try to decrease the flow of current, then what is the job of an inductor? The job of an inductor is to oppose the change of current. That's what the statement states, no? L is inversely proportional to di by dt. What does di by dt mean? Change in current with respect to time. So what does an inductor do? Inductor will not allow the change of current to take place with respect to time. Because inductance has something to do with what? Inductance has something to do with inductor, and inductance itself is coming into picture because of change in current. So what will an inductor do? It will not allow the current to change with respect to time. This is a very, very, very important point to be understood. So what is the conclusion? Can you tell me? Inductor does not allow current to change with respect to time. Okay. One common mistake is, if I ask a question of why is an inductor there, they say to induce EMF. Inductor's job is not to induce EMF. Inductor's job is to decrease the change in current. So what do you say? Does not allow the current to change with respect to time, or it's going to oppose the rate of change of current. Both are same. When I say rate, it is something with respect to time. Are you able to understand the statement? Now, L is equal to E divided by dA by dt, right? Now I'm going to give a unit to it. We need to understand what is the unit that is used to measure inductance. So for example, for resistance, what will you do? You'll write it as volt per ampere. Volt per ampere as a combination is written as ohm. You will put that omega. In a similar way, for inductance, right? If I want to write the SI unit of inductance, EMF is measured in volt divided by current is measured in ampere per second. So this volt second per ampere is given a name called as HENRY, which is called as Henry, right? Which is represented by the symbol capital H because it's a name. Okay. You remember for capacitance, what you have? C is equal to Q by V. Q is measured in terms of coulomb, volt. V is measured in terms of volt. Coulomb by volt is called as farad. It's a name derived from Faraday, right? So you have something called as farad, which is represented by the symbol capital F. But if you see most of the problems, you see capacitance will always be in terms of microfarad. We will never deal with a capacitor which has the value directly in farad because the area will be very large. You cannot design it. So in practical applications, you see all the capacitors that we are going to use, will have a capacitance of few microfarad. In a similar way, all the inductors that we are going to deal here will be in terms of millihenry. So Henry is going to be the SI unit, but mostly in practical applications, the value of L will be in terms of millihenry. That is why most of the problems you will see this happen. Are you able to get a context of the story? Are you able to understand why we are studying this? இல்லடா நான் என்ன சொல்றேன்னா see work done is measured in joule. அந்த ஜூல் எப்படி வருது? ஃபோர்ஸ் இன்டு டிஸ்பிளேஸ்மெண்ட் இன்டு காஸ்ட். ஃபோர்ஸ் என்னது? நியூட்டன். டிஸ்பிளேஸ்மெண்ட் மீட்டர். ஸோ நியூட்டன் மீட்டர் ஜூல்னு சொல்ற. டார்க் என்னது? ஃபோர்ஸ் இன்டு அதுவும் நியூட்டன் மீட்டர் தான். அங்க ஜூல்னு சொல்றோமா? இல்ல நான் தான் சொல்றேன், வராது இல்ல. ஸோ இன்ஸ்டெட் ஆஃப் தட் நியூட்டன் மீட்டர் யூ ட்ரைங் டு கிவ் அ கம்பைன், அந்த காம்பினேஷனுக்கு ஒரு பேர் கொடுக்க பாக்குறல்ல, அந்த காம்பினேஷன் கொடுக்குற பேர்ல அதே மாதிரி தான் இங்க சி பை விக்கு கொடுக்குற பேர் ஃபேரட். ஸோ யூ டோன்ட் திங்க் இன் டர்ம்ஸ் ஆஃப் சார்ஜ், அது மாதிரி யோசிக்க கூடாது. If there is a combination of, you are able to measure the coulomb per unit volt, and the unit பேர் farad. So அதே மாதிரி if there is a unit Newton which is causing a displacement of unit meter or else unit displacement, அதுக்கு பேர் தான் வந்து 1 ஜூல்னு சொல்றோம். ஸோ அந்த காம்பினேஷன் கொடுக்குற பேர். புரியுதா? Those are online. Did you understand?
Yes, sir.
Yes, sir.
Very good. Please make a note of it. இந்த சாப்டர் முடியலடா ஸ்கூல்ல. தெரியாது, இந்த சாப்டர் ஐடியாவே இல்லை. ஓ, 5th அப்புறம் டைரக்டா 8th இல்ல? Is tomorrow a holiday for everyone? Is it holiday? Everyone. எங்க ஒருத்தர் இருக்கான், அவன் மூஞ்ச காட்டு. ஆ ஏன்? ஆல் இண்டியா ரேங்க் 1, AR1. தீபாவளிக்கு லீவ் கொடுப்பாங்களா? நாளைக்கு ஸ்கூல் போறியா அங்க போறியா? ஸ்கூல் ஆனா லீவா? ஸ்கூல் க்ளோஸ்டா? Wednesday school closed. For you guys, tomorrow and day after tomorrow, is it closed or only tomorrow? DAV I heard. உங்களுக்கு இருக்கா? Wednesday school இருக்கு. எது கேட்டேன்னா ஒருவேளை ஸ்கூல் இல்லைன்னா I thought I can have a morning session. முடிச்சிடலாம்டா காலையில. ஈவினிங் படத்துக்கு போ. என்ன சரி. பட் அவன் வரணுமே உன் ஃப்ரெண்டு. பரவாயில்லையா? வீடியோ பார்க்குறியா? நீ எப்படியும் மேக்ஸ் பண்ண மாட்டேன், என் டைம் வேஸ்ட் பண்ற. மேக்ஸ் கிளாஸ்லயும் உட்காந்து பிசிக்ஸ் படிச்சுட்டு இருப்பேன். அப்பா விட்டுரு, பிசிக்ஸும் விட்டுருன்றான். பிசிக்ஸும் விட்டுருன்ற, நாளைக்கு வீடியோ பார்த்துக்கோன்றான். என்ன சார்? சரி, கேன் வி ஹேவ் இட் மார்னிங்? ஒருத்த நாள் தான் ப்ராப்ளம் எல்லாம். என்ன பண்றதுன்னா, ஐ யூ டன் ரைட்? காலையில காலையில கன்னடாவா? சரி, are you done with copying this? இல்லையா? சரி, சீக்கிரம் முடிச்சு. Those are online. Are you done copying?
Doing, sir.
Yes, sir.
Yeah, write it down, write it. Fluxக்கும் டைமுக்கும் not necessary. Not necessary. Flux can change in any way you want. Not necessary. இல்லையே, that you write it for EMF. அது alternating current. Alternating. புரியல எதுக்கு? ஆமா, EMF டைமுக்கும் சைன் கிராஃப். That is your alternating current. That will be the first thing in the next chapter. They முடிஞ்சதா? Are you guys clear with this? Any doubt? Are you all clear? Right, shall I proceed? Right.
Yes, sir.
Yeah. Right. The next question is, using the same concept, right? So using the concept that we discussed now, what we should derive is, we'll derive the self-inductance of a long solenoid. So if you have a long solenoid, so what is the meaning of that? The radius of the solenoid is going to be very small compared to the length of it. And we know that for a long solenoid, what is going to be the value of magnetic field? B will be equal to mu naught into N into I. Am I right? So our job is to derive the self-inductance of a long solenoid with the expression that we already have. Right? So let us consider a long solenoid of length L and radius small r in such a way that the value of small r is going to be very much less than that of L. Okay. And let's say it has n turns per unit length. And if a current I flows through the coil, if a current I flows through the coil, then the magnetic field inside the coil is almost going to be constant. This we have already discussed. So due to a long solenoid, what will happen is the magnetic field is going to be present only inside the solenoid, and outside it is going to be 0. And its value is treated to be equal to B is equal to mu naught into Ni. So that is what we are going to start with. So what is going to be the value? B is equal to mu naught into N into I. Right. Logic is very simple, okay? So what is that we need to derive? Self-inductance. So you remember this expression, phi is equal to L into I. So what is the flux? Flux is the value that is associated with this coil. So what does this flux represent? It is the amount of flux associated with the coil itself. Here, what is the coil? It is a solenoid. And L is going to be the self-inductance of the solenoid, and I is going to be the amount of current that is flowing through this solenoid. All right. Now, our job is to derive self-inductance, which is L. Can I write this as phi divided by I? But what is the value of phi? there is only one formula for phi, which is BA cos theta. So it is going to be BA cos theta, the whole divided by I. So are you clear with the sequence of steps? Okay. You can write it as NBA cos theta also. Okay, where you have n number of turns. So this is going to be equal to n into what is the value of B that is associated with this coil? It is going to be mu naught into n into I. Am I right? Into area of this coil is going to be how much? So when you look at the coil from this side, it takes the shape of a circle. Though it is a form of a helix, it is going to take the shape of a circle. For a circle, what is going to be the area? It is pi r square, the whole divided by. So when I talk about this area, it is a cross-sectional area, right? So remember, magnetic field is in this direction. Area of the coil is also in this direction. So what is the angle between both? 0. So how much are you going to get? Cos of 0 degrees. Cos 0 is going to give you 1. The whole divided by, can I write it as I? I and I will get cancelled. Done. So what is the sequence we followed? We followed phi is equal to Li, L is equal to phi by I. So for phi, I applied the formula of NBA cos theta, and for I left it as it is. Right? So this will be equal to, can I write capital N as small n into L? Right? Can I write it as small n into L? So small n into L into mu naught into n multiplied with pi r square, and cos 0 is going to be 1. So what will happen here? It will be mu naught n square pi r square L, which is going to be the value of self-inductance that is generated inside a long solenoid. So this is the value. Am I clear with this? Right? So it's a very simple derivation. Done, doc? Have you done copy? Right? Shall I proceed? Those are online. Shall I proceed?
Okay, sir.
Okay. Yeah. So the next concept that we are going to discuss is mutual induction. Okay. So as mentioned previously, when I talk about mutual induction, you need a minimum of 2 coils, right? Where one coil is going to get connected to the battery and the other coil will be connected to a sensitive device like a galvanometer or an LED to detect whether there is an EMF getting induced or not. Am I clear with that point? So having said that, if you observe, we have a coil which is connected to a battery, which is called as the primary coil. So basically, the coil that is connected to the battery is called as the primary coil. And the coil that is associated with a sensitive device is what is called as a secondary coil. Am I clear with this? Now, in the previous case, when we discussed self-induction, we understood the fact that the second coil was not existing. And due to the change of current in the coil, there was an EMF induced in the same coil, which is called as self-induction. Now, what is going to happen here? Now, if I have the battery open initially and I'm going to close it, right? If I'm going to close this battery, then what is supposed to happen? Then the same process should continue. Current is going to increase. Then magnetic field associated with this coil is going to get increased, right? So we know that the magnetic field is going to be in this way, right? The magnetic field is going to be in this way. So when the current is growing through this coil, the magnetic field is going to increase. So the magnetic field that is generated by the first coil will create a flux in the second coil. Am I right? So it will create a flux in the second coil. So the flux in the second coil is going to increase. So what is happening here? The current in the first coil is increasing, due to which there is an increase in the flux in the second coil, due to which there is an EMF induced in the second coil. So it's the same story, except the fact that in the previous case, there was only one coil which was acting as the primary and the secondary. It is the one which was picking the value. Whereas here, what is going to happen? It is going to be the reverse scenario, right? So it is going to be the reverse scenario in such a way that the current increasing will create a magnetic field. The magnetic flux associated with the second coil is also going to change, due to which there is an EMF induced in the second coil. So observe, EMF is induced in the second coil due to the change of current in the first coil. That is why this is called as mutual induction. Am I clear with that? Right? So can I have a textbook once? I want to check which part is deleted. We can make a note of this. There. Right? Shall I proceed? Those are online. Shall I proceed?
Yes, sir.
Listen. Now tell me one thing. In this case, right? So in the previous case, you remember what was the relation we wrote between the flux and the current? We wrote that the flux associated with the first coil is directly proportional to the current through the same coil itself. Whereas here, what is going to happen? The flux associated with the second coil, N252, is directly proportional to the amount of current in the first coil. Makes sense? So N252 is directly proportional to I1. So if I remove the proportionality symbol N252, then what is the constant I'm supposed to introduce? Then the constant I'm going to introduce is going to be capital M. So in the previous case, we used L for self-inductance. Here we'll use M for mutual inductance. But for mutual inductance, you need to be very strong with the subscript, right? So I can write it as M into I1, okay, accepted, but this you'll write it as M21. That is mutual inductance of the second coil due to the current flowing in the first coil. So when you write M21, right, M21 will be equal to N252, the whole divided by I1. Make sense? So N252 divided by I1 is going to be the value of M21. In a similar way, if you just swap the coils and write it, see, I'm taking this as the first coil, this as the second coil. Okay, it is just a symbol. Try to understand. I'm taking this as the first coil, this as the second coil. So M21 will be equal to N252 divided by I1. If I just take the symbols in the reverse order, if I take 2 and 1, then what will happen? Can I write N151 is directly proportional to I2? Then what will I write it as? I'll write it as M12. So M12 is equal to N151, the whole divided by I2. So it's the same logic. But I hope you're able to understand this, right? Now the question is, what is going to be the SI unit for it? So here, what is going to be the SI unit? SI unit is going to be Weber per ampere, right? This Weber per ampere is also called as Henry. So if you see in the previous case, L also we wrote it as 5 by I only. Then we tried to write it in terms of EMF. We got it as volt per. How much did we get? We got volt per ampere per second. That gave the value as Henry, right? Here also it is going to be Henry only. Am I clear with that point? Yes or no? Now the question is, what is going to be the EMF that is induced in the second coil? So can I say that the EMF induced in the second coil is directly proportional to, wait, can I use this expression, right? Can I use this expression and differentiate it? So if I consider d by dt of N252, this should be equal to d by dt of M21 into I1. Am I right? Can I write it like this? So if what is this value going to be? The rate of change of flux in the second coil with respect to time will be the EMF induced in the second coil is equal to, but we know that d phi by dt is negative of E. So I'll write it as minus M21 into di1 divided by dt. So E2 is equal to minus M21 into di1 divided by dt. So M21 will be equal to how much? E21 divided by di1 by dt. So it is exactly the same process that we are following for self-inductance, except the fact that here we are concentrating more on the subscripts. Am I clear with this point? Yeah. Is that clear? So this is what is called as mutual induction, and this M21 is what is called as mutual inductance. Okay, but here also what you're dealing with the same inductors. These devices are what are called as inductors because they will also oppose the rate of change of current. Okay, so like how we did in the previous case, in this case also what we'll do is we'll derive the mutual inductance for two solenoids. Okay, so that part will be the next topic. So that I'll start it in the next class. So tomorrow we'll be mostly completing is what I assume this chapter. Okay, I'll do one thing. Tomorrow I'll solve some problems based on these two concepts. Okay, on Wednesday we'll complete the last topic that will be there, that is AC generator. With that, this chapter is done. Okay. So any other questions?
No, sir.
Okay. And wind up.
Thank you, sir.
Thank you, sir.
Thank you, sir. Yeah, ma'am.